Welcome back. In this video, we'll learn more about MIPS programming and go all the way down to the ones and zeros. The number 32 pops up a lot in MIPS. There are 32 general purpose registers. Each of those is 32 bits in length. Words in memory are 32 bits long. Instructions are 32 bits, and addresses are 32 bits. Here's a list of commonly used assembler directives. While assembly language instructions tell the CPU what to do, assembler directives tell the assembler what to do. In other words, how to convert the assembly code into machine code. We've seen several of these before. We've seen that .data and .text indicate the start of the data and the code portions of the program. We've seen the ASCII Z string is a null terminated string. If we don't want the null at the end, we could just have a plain ASCII string. We've used words to define consecutive words in memory, but we can also define bytes and half words. The .space directive lets us reserve a certain number of bytes in memory. This is sometimes used as space for like an input buffer. We'll talk about floats and doubles later in the course. We'll typically use .align as .align2, which will tell the assembler to put the next item in memory on a word boundary. We'll see an example of this later. Let's look at a few examples of how the assembler directives tell the assembler how to store data in memory. So here we have .word and just one word, and we see that here in memory. The next item is a .word, but it just has one character in it, C, and so we see that's placed in the low order byte, and it takes up the whole word. Next we see an ASCII Z string ABC, and we see that the A, B, C, and the null terminator are here in one word. Note that when you specify a single character, you use single quotes, but for a string you use double quotes. Here are a couple more examples. And recall our format is label with a colon, the storage type, and then any values. Here we're using .byte for 2 bytes A and B. And I have ASCII turned on here so you can see the A and B right here. Then we have the .align2, which indicates that we should not start the next item in the next available space. We should scoot over to the next word, the start of the next word. And now we have .space 4, which just indicates that we should reserve 4 bytes, which is a word. And then we have our null terminated string hello. There are 3 types of operands in MIPS. The first is registers. The second type is a memory location, which could be a label or it could be a register used to hold an address. And the third is constants. You don't get to pick and choose which operands you want to use. Each opcode works with certain types of operands in order. For example, this instruction will not assemble. By the way, sometimes Mars is a little more generous with the syntax, but try to stick to the syntax we discuss in class. Assembly language is very close to machine language. In this next discussion, you'll see that for yourself. Each MIPS instruction assembles into 32 bits of machine code. For all instructions, the first 6 bits represent the opcode. From there, it varies depending on the type of instruction. The good news in MIPS is that there's only 3 types of instructions we need to learn. This simplicity of design leads to fast execution. I've posted the MIPS card in Piazza. It lists the basic MIPS instructions with their opcodes as well as numbers that represent registers. Recall that we have 32 general purpose registers, and we'll only need 5 bits to address 32 registers because 2 to the power 5 is 32. The registers we use most often are the T registers. T0 through T7 are numbers 8 through 15. T8 and T9 are numbers 24 and 25. And S0 through S7 are numbers 16 through 23. The first instruction type we look at is the R type. It's called R because all three of its operands are registers. So first look at this little screenshot from Mars. Here is the instruction that we typed in. It's an arithmetic logic instruction, and so all three of its operands are registers. And notice how it gets first assembled. The register names T0, T1, T2 are converted into their numbers 8, 9, and 10. And actually, you could type this in as your code. I have a preference for using the register names instead of the numbers in code because I think it's a little bit more readable. This part of the screenshot shows the actual assembled code, the ones and zeros written in hex form. Here we see the R format. The first 6 bits, the most significant bits, are the opcode. For R-type instructions, there's both an opcode and a function code. Both of those are 6 bits. In between, everything is 5 bits. So we have 5 bits for our 3 registers. Notice one thing here, that when we type the instruction, our destination register is first, but in this format, it is last. And that's just because these 2 registers need to be read in order to process the information, and then later we write back the result. These 5 bits here are shift amount, which are only going to be used for the shift instruction. So for all other instructions, they're just going to be zeros. Here's a screenshot of part of the MIPS card. And notice it lists the basic instructions in alphabetical order, as well as their mnemonic. It tells which format they use, R, I, or J. You can see that R and I are the most common ones. There's a little bit of information on what the instruction actually does. And then over on the far right side, you see its opcode, or if it's an R type, it's opcode/function code. Here I've blown up the subtract line to show each of those parts. And the way to read this is just to say that the destination register equals the source registers subtracted from each other, RS minus RT. And over on the far right, we have the opcode, which is 0, and the function code, which is 22 hex. Let's practice translating this instruction into machine code in binary. So our instruction is sub S0, T3, T4. And just for reference, I've written the numbers of the registers here on the right. First, we pick off the opcode and the function code. The opcode is 0, and we need to fill 6 bits with that. The function code is 22 in hex, so we write 22 hex in 6 bits of binary. Next, we fill in the 5 bits for the registers, and we fill in the shift amount with 5 zeros. So here we have the binary machine code of the instruction, and generally it's more readable if we put it in hex. So recall that each 4 bits will correspond to 1 hex digit. Here are a list of common load store instructions. We've used load word and store word, but there's also load byte and load byte unsigned generally used for a character, and store byte. There are also load and store instructions for half words, but I don't find those very useful. In addition, we have a couple of load pseudo instructions which we've mentioned. LA for load address and LI for load immediate. Load store instructions use the I format, where RT is the destination and RS is the source. So the address for the load or the store is going to be the constant, which is stored in the lower 16 bits of the instruction, plus the RS register. And that constant can be positive or negative. Then the destination is the RT register. Note again that we write RT first in the load instruction, but it's last in the I format. Let's practice finding the machine code binary for this instruction here. Load into register T0 the contents of memory address found by adding T1 plus 8. The opcode for load word is 23 hex, which will fit into this 6-bit field. Our RS will fit here. Our RS in this case is T1. and our destination RT will fit here. Our destination is T0. The lower 16 bits are for the constant 8. Again, once we find the binary, we want to convert that into hex for readability. Here's a simple load byte, store byte example. First, we define a couple of bytes in memory, A and B, and we see those are placed here. Then we say dot align to, which indicates that the next item should start on the next word boundary. So we'll skip over this part and have a space here, which initially would be zeros before the program is run. So we're loading the address of S1 and S2 into T1 and T2. So we're using T1 and T2 as pointers. Then we load byte unsigned. This again is typically used for characters. So we load the first character, which is going to be A, into T0 and store that out where T2 is pointing. So that will write this first A here. Now we're adding 1 to both T1 and T2 to point to the next bytes, and then repeating the same load byte. So this will load the B here and store it out there. Later we'll learn how to do this with loops. So we've observed before that strings appear to be stored in kind of a backwards way. Here's another example of that. We have a null terminated string, hola, and the H is first. All right, so it turns out that computers typically store things in one of two ways. One is called big endian, which is how MIPS does it, so that the most significant byte, the H, is stored in the lower address byte. And other computers do it in the opposite way. Those are called little endian. So this weird terminology needs a little explanation. It turns out that years ago, someone wrote a paper about these two different storage approaches, and he called them Little Endian and Big Endian after a story in Jonathan Swift's Gulliver's Travels about an argument that people had over which end of the egg to open, the big end or the little end. By the way, some can go either way. That's called bi-endian. An example of that is ARM processors. Arithmetic and logic instructions have an immediate version. The arithmetic and logic instructions all use the R format, but the immediate versions use the I format. So you can see already that the I format is going to be very versatile. Let's look at how to find the machine code, binary, and hex for this add I. All right, the opcode is 8, so the 8 will fit in these 6 bits here. Our destination register is T0, that will go in the RT field, and our source register is T1, which will go in the RS field. The last 16 bits are reserved for the 8. So here is the binary and the hex for this instruction. Next we talk about writing and debugging assembly language programs. Starting out writing assembly language can be a little intimidating and debugging can be frustrating, so I have a little advice to help you out. When writing a MIPS program, particularly if it's a longer one, it's a good idea to first write pseudocode or code in your favorite higher level language, just to make sure you have the logic right. Then I would think about what data you need and reserve space for that in the .data section. And break the problem into pieces, like first input all of your data, process it all, and then output the results. And most importantly, code and test one step at a time. What you don't want to do is type in 100 lines of assembly code and then expect it to work. For debugging, you can take advantage of breakpoints as well as single stepping. And you want to stop and look at registers in memory to see if the program's doing what you thought it would do. It also wouldn't hurt to insert a few syscalls for output at critical points. So to demonstrate this, we're going to write a program to get and store the user's name, greet the user, get a couple of integers from the user, find the sum of the integers and store that, find the difference and store it, and output sum and difference. Here's a code solution I typed into Mars. Let's look at the data section first. By the way, the .text and .data don't need to be all the way over on the left. It can be somewhere in the middle. That's up to you. So notice I reserve words for the numbers the user is going to give me, num1 and num2, as well as the sum and the difference that my program will calculate. I also reserved 20 bytes for the name the user is going to give me. And then I have all of the output strings. I could have given them more creative names, frankly. All right, so for the code, I separated each step with some white space and a comment. So what I generally like to do is write my comments first and leave a lot of space there. And then I can type in one chunk of code and test it before moving on to the next one. I find that a lot of students don't appreciate the value of white space. The white space makes code very much more readable. So you can see there's a logical step here. Here's another logical step here. So the white space and comments make your code more readable, and it won't cost anything in terms of the size of the program. So a program is going to assemble into a certain number of bytes whether you've got comments and white space in there or not. So keep in mind that code number 1 is written for humans to read and secondarily for computers to execute. One of my recommendations is to write and test one section of code at a time. So let me demonstrate that. I'm going to assemble and then look at my code here and find the place where I get the string from the user and then I store it. So it needs to be after this syscall that I set a breakpoint, and you set a breakpoint just by hitting this little button over here. Then you can hit the green button and it will stop at this breakpoint. So let me run. It's going to ask me for my name. I'm going to type Joe. And then it's going to stop right there. And what this does for me is it allows me to find Joe. Here's Joe right here. And so I can figure out if it got the name stored correctly or not. All right, let's run the program, and I want to talk about something in the output. So I'm going to uncheck my breakpoint and run the program. All right, so it's going to let me enter a number. I'm just going to enter a couple of numbers here. And notice that this output is all run together. So there's a couple of ways that we could deal with that. Let me show you one way first. We go back here to edit. And in our strings, we could just put escape new line. And let's see what that does for us. All right, that looks a little better. I want to show you another way to do that. And that is to go down here between where I print out the sum and the difference. And let me insert some new code here. I'm going to output a new line. So the new line character is actually 10, and this is the system call here, number 11, to print a character. And the reason I'm showing you this way is that in future homeworks you might want to also output a space in addition to a new line. So let's see what that looks like. All right, so we got 2 new lines actually there because we still have the new lines in the strings themselves. All right, let me show you one more gotcha here, and that is if a person, instead of using space to reserve 20 bytes, they get confused and they say byte 20. This will actually just store 20 in 1 byte, and it will cause some problems, as we'll see. And this kind of problem can drive you nuts to debug because you're going to think the problem is in your code when the actual problem is up here in your data section. So let's see what happens. So I've set a breakpoint at the same point after the name is retrieved from the user. And let's look at memory first. So this word is for num1, this is for num2, This is for sum, and this is for difference. And this is where my name buffer was supposed to be, but we see this dot right here is actually that 20. So keep your eye on that as we do a run here. What is your name? Joe. And we pause right here, and we see what happened is that my name is actually overriding my message 1. So the takeaway of this part of the lecture is that coding in assembly language is not like coding in a higher level language, in a modern IDE that tells you where the errors are. You have to dive in and see what's happening in memory and your registers step by step. So today we got a little more practice writing MIPS programs and looking at the static memory section for how we store items. We also got practice down at the 1s and 0s, hand assembling MIPS instructions, and then some advice on running and debugging MIPS programs. Until next time, happy coding!